Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So the first of the talks for this session is by Alan Orlitsky and Ananda Suresh on competitive distribution estimation. Why is Good-Turing good? And Ananda Suresh will be giving the talk.
So Ananta, on behalf of the NIPS Program Committee, we just wanted to congratulate you and Alon for a Best Paper Award. Thank you.
I would like to thank all of you for being here, and also the NIPS Organization Committee and the Program Committee members for giving me an opportunity to speak in front of such a large audience, and also for the award and definitely a heavy check. So, okay. All right. So I'll be talking about competitive distribution estimation. This is joint work with my advisor, Alon Orlitsky. And I would also like to mention that I want to thank all the reviewers for their very helpful comments. In particular, some of them gave very vivid analogies. For example, one of them said, you can say why you should not all driving around in a tank in Montreal. That fact can be explained by our approach. We'll come back to this later. So here is an outline of the talk. The goal of this talk is to understand the basic statistical problem of discrete distribution estimation better. Despite it being so basic and fundamental, there are still a lot of open questions, and we would like to address one of them. So we'll start with the more theoretical, well-understood, traditional min-max approach, and move on to the more practical competitive approach. And I hope to make a good case why we should look at competitive estimation. In this competitive approach, I'm going to show fast convergence results that are independent of the underlying support size. To do that, I'm going to look at an estimator that was due to statistician I.J. Good and father of computer science Alan Turing, which they proposed way back in 1940s when they were cracking the Enigma code. So let's start with the first part, which is min-max estimation. To understand the problem setup better, let's start with a very simple example, which I'm sure all of you know. Suppose you have a biased guy, and you're interested in finding the probability of each side. How do you do it? You all toss it a few times and count how many times each side appears. It's very simple. And if I ask you probability of a particular symbol, let's say symbol phi, you count how many times it appears, and probably say, in this example, it's 0.2, because this is a well-understood empirical estimate, which for a symbol just assigns the probability proportional to the number of times symbol appears. And we know that by law of large numbers, this converges to the actual probability. The question we want to first ask is it a good estimator? To do that, I need some definitions. I need to say, what do I mean by a good estimator? Let P denote the underlying discrete distribution. It can be over species in an ecology application, or it can be over words in natural language processing. For simplicity, I'm going to assume it's over integers, 1 up to k. Let Xn denote n independent samples distributed according to P. And let Q be a proposed estimator, which depends on the underlying samples Xn. As I said before, we want Q to be close to P. And in this talk, I'm going to use expected Kullberg-Leibler divergence, or KL divergence, as a measure of closeness. More specifically, let R and PQ denote the expected KL divergence between the underlying distribution P and the estimate Q, and the expectation is over the samples. So this has two nice interpretations. For example, if you're doing online prediction over discrete distributions, this is nothing but the expected log loss. And in information theory, this has an operational meaning. It's the additional number of bits you need to compress a source P if you do not know P. So far, I just told you how good is an estimate for a particular distribution. It's not clear which distribution you want to optimize for. The popular or the most standard min-max approach optimizes for the worst distribution. More specifically, if delta k denotes the set of all distributions over k symbols, the goal is to minimize the maximum loss over all distributions. Let Q star denote the min-max optimal estimator. Q star can be found. There was a recent paper in 2002 where they gave an explicit formula. However, it's not used in practice, and the question is why. To illustrate why min-max might not be the best approach, I'm going to give you this simple example. Here I have two estimators, blue and yellow, and 5 distributions, P1, P2, P3, P4, P5. And I'm showing the loss of an estimator for every distribution. First, observe that the worst loss for the blue estimator is less than the worst loss for the yellow estimator, because the distribution which dominates is P1. Therefore, the min-max optimal estimator is the blue one, that is Q prime. But if I ask you to pick between blue and yellow, most of you will observe that the yellow estimator incurs a small loss for all distributions P2, P3, up to P5. And for P1, it incurs a small additional loss compared to the blue estimator. So most of you will pick P1. But if I forget told you that P1 rarely or never occurs in practice, then all of you will probably pick the yellow estimator. A more vivid analogy is because of one of our reviewers. Suppose you want to find the best vehicle which works for all terrains. If you follow a min-max approach, you find the best vehicle that's optimized for the worst terrain, and probably you're going to pick something like a tank. And clearly, none of you want to drive around a tank in Montreal. And our goal is to come up with a single vehicle which is near optimal for every single terrain. To do that, I'm going to look at computative distribution estimation, which in statistics is also called adaptive min-max estimation. The goal is to estimate each P as well as all possible human design estimators. So I'm being slightly vague here. To make it more concrete, we are going to compare ourselves with a super estimator, which has some additional information. Clearly, if you can do better than a super estimator, which has additional information, we do as well as any human estimator designed by anyone else. And for this analogy, or for this formulation to work, note that we can compare ourselves with any superhuman estimator with any extra information. There's no particular choice. And we pick one which knows the underlying probability multiset. That is, the one which knows the underlying distribution up to a permutation. Let me give you an example. Suppose the underlying distribution is P, with symbol probabilities 0.4, 0.2, and 0.4. The super estimator knows the multiset, which is just the set 0.4, 0.4, and 0.2. So it essentially knows the entire distribution, but it just doesn't know the assignment of probabilities to symbols. Such a super estimator, since it knows the multiset and it doesn't know the distribution, it tries to optimize its estimator for all possible permutations. In particular, let R and P denote the min-max loss of this super estimator, which knows the underlying multiset. Our goal is to come up with an estimator Q, which is uniformly close to this super not realistic super estimator, and let R sigma n be this difference. In the figure, it's more clear. The min-max estimators just tell us that the performance is below the blue line, but it never tells how close is it to the best estimator. But our approach, we try to quantify how close you can be to the super estimator. Okay. Analyzing the super estimator is tricky because we don't know all. Even finding an explicit formula for the super estimator takes some effort, but It's easy to see that such a super estimator should assign same probability to all symbols that appear the same number of times. For example, if you see two symbols, say if you see the sequence A, B, B, A, C, E, notice that both symbols A and B appear twice, so it would assign the same probability. Suppose now I give this estimator some additional information. I actually tell it the exact distribution. But it still has to satisfy the property that it assigns the same probability to symbols that appear the same number of times. What would it do? Since it knows P of A and P of B, and it wants to be close to that, it probably also assigns both symbols QA and both for symbols A and B, it assigns the average, P of A plus P of B by 2. In general, we can prove that by the properties of KL divergence, if a symbol appears t times, we assign it the average probability of all symbols that appear t times. Here, S of t denotes the sum of probabilities of symbols appearing t times, which we do not know in advance. Only this unrealistic super estimator has this additional information. Therefore, we can substitute it with an estimator, S hat, and we show that the additional loss we incur with respect to this super estimator is the computative additional loss we incur with respect to this super estimator is upper bounded by the KL divergence between the actual S and S hat. Notice that both S and S hat are random quantities. So again, we take an expectation over the underlying samples. Therefore, our goal is to estimate ST as well as possible. The insightful or the genius observation of Good and Turing is that on an average or in expectation, expected value of S of t is exactly equal to t plus 1 by n times expected value of phi t plus 1. To recall, S of t is the sum of probabilities of symbols that appear t times, and phi of t plus 1 is the number of symbols that appear t plus 1 times, not t times. The Good-Turing estimator is therefore just you drop the expectations and you use that as an estimate. So the Good-Turing estimate is nothing but t plus 1 by n times phi of t plus 1. This was proposed by Good and Turing way back in 1953, and later it was popularized in statistical NLP by a paper by Gale and Sampson. However, theoretical guarantees were largely unknown. There's a recent paper by McAllister and Shapire where they showed that Good-Turing estimator can efficiently estimate quantities such as missing mass or probabilities of symbols that appear once, twice, and so on. There are subsequent developments by Druk and Mansour, and recently by Acharya et al. In information theory, Orliksky et al. Showed that Good-Turing estimators can be used to efficiently compress distributions over large alphabets. But it still remains to be shown that whether Good-Turing estimator is min-max optimal or even if it is computatively optimal, which is our result. We use some techniques such as Poissonization and some strong properties of KL divergence and improve the previous bounds and show that the computative regret of a Good-Turing estimator is at most 3 divided by n to the 1/3. There's a smaller one term there, which is at most 3 even for n like 500 or 1,000. Further, we can show that an improved estimator incurs a computative regret of at most 1 over square root n. And all these results are independent of the support size k. I'm not hiding any factors of k in any of these equations. Hence, even if you have like billions of words, and if you have just 200 samples, we'll still be close to the best you can do, plus 1 over 200 to the 1/3. We also show an information theoretic lower bound that the computative regret for any estimator cannot be smaller than 1 over n to the 2/3. If you're still not convinced why this is good, let me show you some simulations. So far, I talked about super estimators and showed you pictures of cars and so on. But let's plot the performance of the estimator for a useful distribution. Here, I'm taking zip or a power law distribution with parameter 1.5 with 10,000 symbols. And I'm plotting the expected KL divergence as a function of number of samples. Clearly, if you keep taking more and more samples, all the estimators do well. But observe that the green curve, which is the Good-Turing estimator, is very close to the red curve, which is the super estimator, which has additional information. In fact, they're almost identical. All the min-max or the Bayes motivated estimators, such as Bayes-Sawyer or Laplace or Adwan estimator, the estimator due to Krzyzewski and Trofimov, they all perform significantly worse. One might argue that this is just an aberration of zip 1.5 distribution, which I'm looking at. But if you plot it for other distributions, like take uniform or like a step distribution with 2 steps or zip with other parameters, for all these more practically useful distributions, you see that the Good-Turing is really, really well compared to the other estimators. If you're still not convinced, I'll tell you one last observation. Suppose you want to do binary classification of categorical data. You have 2 training sequences, xn and yn. Xn distributed according to an unknown distribution P, yn distributed according to an unknown distribution Q. And if I ask a test symbol Z, is it according to P or Q? Suppose these are the sequences. The first sequence is AB, AB. The second one is A, B, 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 B. And if I say the test symbol A, is it more likely occurred from the first one or the second one? Probably most of you would say you want to assign it to a distribution where it occurs higher number of times. However, this is strictly suboptimal, and we can do better. Here I'm plotting the same results for 2 distributions, zip, where P is zip 1 and Q is zip 1.5. And the blue curve is the empirical estimator, where you assign it to the sequence where it appeared more number of times. The red one is a Good-Turing version of the estimator for pairs of sequences. As you can see, we clearly do better. In fact, we at least gain like 0.04 for many distributions for moderate values of n. To conclude, if you I told you min-max estimator is like coming up with a tank, but Good-Turing estimator is like a transformer. Whichever situation you are in, it adapts to it. So clearly, if any of you can buy a transformer, you'll buy it, I guess. So Good-Turing is practical. Yeah, thank you.
Thank you. Thank you. If you have questions, please do come up to the mics and give your question.
Hello. Thanks for a great talk. I guess first question, or just a question is, you did your analysis assuming one particular superhuman estimator where you knew what the actual multiset was, and then you could say, hey, you know, this is what that superhuman estimator would have, and Good-Turing does the empirical version of it. What other superhuman estimators could you use? What would
So we looked at this one which knows the probability multiset, because sometimes you know that words follow like a power law distribution. And what we're showing is essentially even with that extra information, you cannot do much better compared to Good-Turing. But the same results holds for any other super estimator which knows any function of the multiset. Like, for example, even if it knows just the entropy or the sparsity or any other such functions, we still do, but we are still complicated, yeah. I hope I answered it.
Okay, thank you.
So nice talk. I just have one question. So why is your competitor, the oracle which knows the multiset, why is that a natural competitor? And you know, if you compete against something better, can you do better than better than the results you have? Because there seems to be a gap between your lower and upper bounds. So
actually, I think it's our analysis, and I believe the lower bound is better. Yeah, I mean, is the correct one. And I also believe the estimator which we propose actually achieves that lower bound, but we just don't have a proof. And regarding the question, why do we look at this particular super estimator? The reason is we feel in many applications you know that it follows roughly like a power law or an exponential law, and hence we looked at this. But you can ask the same question for many other super estimators.
Yeah,
Thanks.
yeah.
Sorry?
I said I agree. I was just curious. But
Okay.
Thanks.
Yeah, thank you.
Great. Thank you very much. Let's clap the speaker again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.